Hi there. So today what I'm going to do is I'm going to talk about what I'm calling section 5.0, which is the skills refresher for logarithms. Okay, so what I've done so far here is I've just written all of our properties of logarithms that hopefully you've seen at some point in your existence. Okay, we will be practicing these in the context of each section, but I really like to go through the skills refresher so that we're comfortable with exactly what we're going to need to do in this section. So what I plan to do is just briefly go through each of these. Okay, now you may or may not remember, and I will talk about this in section 5.1. The whole reason why logarithms come up is because we want to talk about the inverse of our exponential function. Okay, I'll go through all of that again, but recall that when you have a function that's one-to-one, an inverse exists. And we'll go through how to find the inverse, but what we see is that we gain this equivalence. Okay, so this is the way we write the inverse for our exponential function. So if our function is, say, a to the x, the inverse function is log base a x. Okay, now again, I'll go through it in detail of that in section 5.1, but one of the things that we see is we come up with all of these different properties of our logarithms. Now, the general way you write the log is this is the log, that's the base, this is what you're taking the log of, that's your domain, and that is your range. The restriction of your base is it's got to be positive. Two things that you've seen before is that there's two logs bases that come up extremely frequently. And these are actually the two bases that your calculator can compute. One base that comes up extremely frequently is log base 10. It comes up so frequently that when we just write log with no base, by default it's log base 10. The other base that comes up extremely frequently is log base e. Recall e is our irrational number. That is about 2.7. Okay, we saw that when things are compounded continuously, we use a base of e. Well, because that comes up so frequently, we also have our log base e. Our log base e is called our natural log. And the way we write our natural log is we write ln. So whenever you see ln, that means log base e. Okay? So, some properties of logs that come up very frequently. Well, when you're taking the log of the product, you can break that up as the sum of the logs. The log of the quotient is the difference. And I think this guy is probably our most useful formula. When you have the log of something raised to a power, you can bring your power down in front. Okay, this is a really important equality that we have. All right. Now, just to motivate a couple of these, for example, whenever you take the log of 1, whatever your base is, it's always equal to 0. Okay, whenever the base of your log matches with what you're taking the log of, it's just 1. When the base matches here and you have log base 10 of 10 to the x, you just get x. Same with the log base e of e to the x, you just get x. This is what it looks like in general. And similarly, and I'll show these to you when I show you about the fact that these are inverse functions, these essentially use the ideas that when you do a function and then you do the inverse, you get back to where it started. So essentially, here you're starting with x and you're taking the log of it, while the inverse of the log is 10 raised to that power, and that's why you get what you started with. Okay? And these work for the exact same reason. You start with x, you put it in the exponential, you put them in as inverse, you get back to where you started. Okay? So we'll go through the ideas behind these, and I'll prove some to you in more detail, but right now in this section what we would like to do is just practice them. Okay? The way you do justify them is you have to use this equivalence. This IFF means if and only if. In other words, y equals log base a of x tells you a to the y equals x. Similarly, a to the y equals x is equivalent to saying y equals log base a of x. Okay, so for example, suppose we wanted to look at the natural log of 1. I'm just going to show you, yeah, that's equal to 0. Okay, suppose we wanted to evaluate that. Well, remember, we know that's a base of e, and if we want to know what that's equal to, I'll call that p. Okay, whenever you want to know what a log is equal to, what you're going to see is that we're going to want to change it to equivalent exponential form. So if we do that, using this, you take your base raised to what's on the other side, and that's equal to what you're taking the log of. In other words, e to the power of p is 1. Well, e raised to what power is 1? Anything raised to the 0 power is 1. That's why the log of 1 is 0. Okay? In a similar manner, I'll show you log of 10. Suppose we have log of 10 and we want to know what that's equal to. Well, I'll call that W right now for no better reason than because today's Wednesday. Okay? Well, remember, when you don't have a base written and you have it written as log, it's log base 10. The way we solve for W is we change this to equivalent exponential form. So we say 10 to the W power is 10. Well, you have two things with the same base set equal. The exponents must be the same, and therefore you get 1. Those aren't things that I'm going to have you prove to me, but I want to show you that we can justify the proof of these statements. So what I want us to do now, using these properties, are just do a bunch of different examples, playing with them. I urge you to have them in front of your face when you are playing with them, because that will help you familiarize yourself. Okay? So, let's play. The first example that I want to play with, we're going to evaluate a bunch of these without a calculator. So, evaluate without a calculator. So the first one I'm going to do is the natural log of the natural log of e. Okay? All right, whenever you see parentheses in mathematics, you always start there and you work inside out. The natural log of e. Well, what is the natural log of e? Using our properties, we know that that's equal to 1. So in place of that, I'll put 1. What is the natural log of 1? 0. Okay? If that's funky, don't stress. Okay, we're going to practice a whole lot of these. Now, what if I want us to find the natural log of 1 over e to the 5th? Well, you might wonder what property to use. Well, this is why you watch these videos and see me work through examples. Notice I'm taking the log of a quotient. So what I'm going to do is rewrite it as the difference of the logs. I take the log of the numerator minus the log of the denominator. From here, I'm going to use my properties. What's the log of 1? Well, that's 0. What is the natural log of e raised to a power? It's just that power. So the answer to this guy is -5. Okay, let's do some more. What if I want to do this example? How about this? What if I want to compute e to the natural log of 3 minus the natural log of e? Okay. Well, what is e to the log of 3? E to the log of x is x. So we get 3. What is the natural log of e? That's 1. So we get 2. I guess it could be kind of a dorky way of saying, hey, I've got $2 in my pocket. You could say, I've got e to the natural log of 3 minus the natural log of e dollars in my pocket. Anyway, what if we have this guy, 10 to the log of 7? Notice I don't have a base written here, so by default, it's a base 10. When these guys match up, we're in this situation, and this is just 7. Okay, now what if I have this? The log of 1 divided by the log of 10 to the 5th. Now, however tempting it might be, do not write this as a single log of 1 over 10 to the 5th. Notice, here we're taking the log of a quotient. That's different than saying log of something in your numerator and log of something in your denominator. Fortunately, we can still evaluate this. Okay, what's the log of 1? 0. The log of 10 to the 5th is 5, but 0 divided by anything is 0. All right, let's do another one of these. One more of these evaluate without a calculator, at least for now. What if, oh, this is a cute one. What if I have the square root of the log of 10,000? Okay, first off, I can rewrite that as the log of 10,000 raised to the 1/2 power. Okay? Now, this isn't quite the same as saying this property here, because notice with this property here, what you're taking the log of is raised to the exponent. Notice here, this whole exponent applies to everything in parentheses. So, let's ask ourselves if we can simplify what's inside. Well, notice this is a log base 10, and aren't we taking the log of 10 to the 4th power? Now, log base 10 of 10 to the 4th, those guys cancel, so you're left with 4 to the 1/2 power, which is the square root of 4, or 2. Okay, next, what we're going to do is practice using some more of these. Right now, we're going to practice with this equivalence right here. Okay? I'd like to just keep those up there, so I'm going to keep erasing over here. So, the next example next two examples that I would like to do, we're not solving anything. What we want to do is we want to rewrite this exponential equation in equivalent log form. That's where we're going to use this equivalence. So, for example, if I have 10 to the 0.477 power, we're given that that's equal to 3. Okay? We're not solving anything. All we are doing is rewriting this in equivalent exponential form. So notice here my a is 10. My y is 0.477, and my x is 3. So plug these values in over here. So y is 0.477 equals log base 10 of 3. This is exactly what they're looking for. Okay, let's do one more. Now, I'll do this up here. Let's do e to the 2x equals 7. All right. Well, what's the base of our log? It's a base of e, so I write natural log. Okay, now notice here, this exponent is what goes on the other side of the equation, and what you're taking the log of goes right there. And again, e to the 2x equals 7. Okay? Now let's go the other way. Now what we're going to do is we're going to rewrite our log equation in equivalent exponential form. Again, it's just getting us refamiliarized with this equivalence. So let's do this example. ln of x equals -1. If it helps you initially to write that as log base e equals -1, that is fine. Okay? Now to write this in equivalent exponential form, the base raised to the other side equals what you're taking the log of. In other words, e to the -1st is equal to x. And that's all we're doing here. Okay, next what we're going to do is play around with these three properties here. Okay, so let's do these. I actually believe that I can erase these guys over here. All right, so what we want to do for the next few examples is we want to, if possible, write the expression. We're going to be given things that are either multiplied, divided, or raised to a power, and we want to write them as the sum or difference with no products, quotients, or powers. For example, excuse me. Let's take log 2x. Notice I'm multiplying two things, so I can rewrite that as log of 2 plus log of x. That's it. That's all you need to do here. Okay, let's do another one. What if I have log of x squared plus 1 over x cubed? Now I've got the quotient, so I can first rewrite that as the log of my numerator minus the log of my denominator. Now, I claim in this case I'm not quite finished. Why? Because this guy's as simple as he can be. That's the log of x squared plus 1. The thing is, the instructions said that we want to write this without having the logarithm of products, quotients, or powers. And notice we have a power here. I'm going to use this third property, so I'm going to say that's minus 3 times the log of x. Okay? I can't take this exponent 2 out of there because it doesn't pertain to everything that I was taking the log of. Okay, what about this example? What if now I'm taking the natural log of the square root of x minus 1 over x plus 1? I know this looks nasty, but remember, we're not solving anything here. Well, the first thing that I would do is I would rewrite this as the natural log of x minus 1 over x plus 1 to the 1/2 power. Okay? Notice I have the log of something raised to a power, so first thing I could do is bring my exponent down in front. In other words, that's 1/2 times the natural log of x minus 1 over x plus 1. Am I done? I'm not done. I've gotten rid of the powers, but now I got a quotient still. So I would write that as 1/2 times the natural log of x minus 1 minus the natural log of x plus 1. Now, you could either leave it like that, or you could bring your exponent in. Either one is entirely acceptable. Notice I referred to this as my exponent because that was where the 1/2 initially came from. Okay? Now, it's a totally reasonable question to say, oh my gosh, Lauren, this seems like such busy work in math. Why are we doing this? Well, it turns out, you guys, that these properties are really useful in calculus when you want to do calculus on your log functions. Okay, so I assure you this isn't just silly math busy work. This is really important, especially if you're going on to calculus. Okay? Alrighty, let's do one more example of breaking things up this way. Okay, the next example that I would like to do is how about the natural log of x squared divided by the natural log of x plus 2. Now, notice you can't break this up into a difference of logs, again, because you're not taking the log of a quotient. What we have is a quotient of logs. So the best we can do is just deal with this power. The best we can do is write that's 2 log x over the log of x plus 2. Again, you can't break this up because it's a sum. You can only break it up when it is a product. All right, now what we're going to do for our last few problems is just go in the reverse direction. We're going to start out with things in this form, and what our goal is for these next few is to write them as a single log. Okay? So the instructions for these last few examples are just to write them as a single logarithm. In other words, we want to write the word log one time. So let us take this. What if I have the natural log of x squared minus the natural log of x plus 10? Now notice, he wasn't as simply written as he could have been. Okay? If he was as simply written as he could have been, it would have read 2 log x minus that guy. Okay? And then what we'd have to do is bebop that guy and make him up in our exponent again. So, we want to write log one time. Well, I'm subtracting, which means I take the quotient. And that is it. All right, what if I have this? Log of 3 plus 2 log square root of x. Again, our goal is to just write the word log one time. Now, you can do this all at once, or you can do it step by step. For our purposes at this point, I'm going to do it step by step. The first thing I deal with is the numbers in front of my logs. Why? Because remember, if there's a number in front of the log, you can make him the exponent. And this one comes out to be really pretty cute. Log of the square root of x, and then we square it. Now, why would I tell you that this is cute? Well, this is cute because we can actually simplify this. Using our properties of exponents, isn't that x to the 1/2 power squared? And when you raise something to a power, raised to another power, you multiply your exponents. So isn't this the log of 3 plus the log of x? Last but not least, log plus a log, you multiply. This is the log of 3x. All right, let's do a couple more. Let's take this guy. What if I have, this is going to look pretty nasty, but don't worry about it. 2 log of 9 minus x squared minus log of 3 plus x plus the log of 3 minus x. And I'm going to have to erase these. Okay, boy, where to begin with this one? Well, one thing we could do is say, well, we got a number in front. Let's make him our exponent. Log of 9 minus x squared squared. Minus, now notice, you guys, I'm subtracting this whole quantity. So what I'm going to do is acknowledge my parentheses right now as well, because I know a log plus a log is the log of the product. Now I have the log of this minus the log of that. So I can write that as a single log because I have 9 minus x squared squared in my numerator. And then I have 3 plus x, 3 minus x in my denominator. Okay? Now, if this wasn't beautifully factorable, we would be done. Okay? But I need to point out something here. Okay? We can actually simplify this further. Why? So we're done with our properties of logs. Okay? But why can we simplify this further? Well, 9 minus x squared squared, I'm going to show every bit of detail. Okay, when you square something, right, it's written twice. The thing is, I see that this is the difference of two squares, which can be factored just like that. So from here, I'm just going to factor one of them. 3 plus x, 3 minus x, and, well, we could do it twice, or we could just write 9 minus x squared. Let me put the log in front. And then we have 3 plus x, 3 minus x. Notice those cancel. So this really simplifies to that. Okay, I know that seems actually very tricky, but remember, only a couple things used our logs. Okay, what used our logs? Well, bringing the number from in front to an exponent. And here, that means we were taking the product because we were adding in here. Now we have a difference of logs, so we wrote it as the quotient. Okay, from here on out, it was just playing a little bit with our algebra. Alrighty, last example for this section. And again, don't worry, as we go through each of the sections in Chapter 5, I will re-explain these rules, I'll re-explain where the word log comes from, etc. Okay? So our last example is 2 natural log of e to the square root of x. Now, we could do this in a couple of different ways. Okay, and I'll actually show you both ways to show you that you get the same thing. Okay, one way you might look at this is say, well, wait a minute, I know that this uses a property, right? The natural log of e raised to a power is equal to the power. So I can rewrite my 2, but I know that the natural log of e to the square root of x is just the square root of x. Okay, suppose you wanted to approach this a different way. Okay, I'll rewrite it out. Let's do this. Okay, well, you might look at the number in front and say, well, wait a minute, he becomes my exponent. So I have the natural log of e to the square root of x squared. Okay? Again, you don't have to do this both ways. I just want to show you that no matter which way you approach it, you're going to end up in the same place. All right, now let's look at this. When you've got something raised to a power, raised to another power, what do you do to your exponents? You multiply them. So the square root of x times 2 is literally the square root of x times 2. And now if you recognize, oh, the natural log of e raised to a power is precisely the power, sure enough, you get the same thing. Okay, so I hope this kind of loosened you up. And again, these properties will become a lot more clear as we go through this chapter. Thank you.